Okay, so rough API for signing. Actually pertains to your last question. So rough API will be generate the key, the secret, find a public key from the secret, sign something with the secret key, sign a message with the secret key, and then verify a message. Verify a signature is a public key signing a message. I mean, this is the public key counterpart of the secret key, but given a signature, did the secret key, whose counterpart is this public key, sign this message? Sometimes you find that the message has to be fixed length, maybe 32 bytes. Sometimes the message is allowed to be any length. For example, in ED 25519, the message can be any length, and internally it uses, I don't know, SHA-512 or something to boil it down into a fixed length. Whereas in ECDSA, the message has to be 32 bytes. For our purposes, it doesn't matter. We just assume that if we have a long message, we're going to hash it down to 32 bytes anyway. Good. Also, as I mentioned in the previous answer, you don't always have to put the public key in. For purposes of an example API, we'll just say sometimes you do, so I may as well put it in to make it general. Sometimes you get the public key out as an output of the verify. Like, it will look at the message, look at the signature, and if it's valid, it will give you the public key that signed it. Sometimes the signature actually essentially contains that information. Sometimes it doesn't, depending on the cryptography you're using. Okay, let's look a little deeper into this. Where did I put it? Yeah. Okay, so we're familiar. This is back in the Rust shell. Nothing changed from before. First, we'll generate a key pair. We have the substrate stuff already put in. When we generate a key pair, we get three things back. This pair object, which is the key pair, the secret and the public. A mnemonic, basically a set of words, which will regenerate the same key pair. If we want to regenerate it again, or if we want to store it. And the raw seed, which is for use with the internal stuff. So there are some operations that we can use the raw seed for. For now, we don't really need it. That should work. Are you going to use the SR25519, also known as Schnorr Ristretto? Yep. Okay, can you not see it at the back? Yeah. Okay. Is that better? Good. Okay. So let's have a look at what we've got back. First thing, let's look at the mnemonic. So this is the key. This is the phrase, which if we use it, if we feed it back into the API at some later date, should give us the same key. There you go. It's actually based on a standard dictionary. I think there's, what, 12 words there. I think 12 is okay, though we tend to recommend 24, which gives, I don't know, about the right amount of data, like about the right amount of entropy, about 256 bits. Good. Now let's regenerate the another key from this phrase. So to do so, we'll call the other key same pair, and the same raw seed, or at least it should be the same. Ah, yeah. This does need a reference. Okay, good. So let's look at some of this data. First, we'll check out the raw seed, see what's in there. And turns out it's a bunch of bytes. Let's have a look at that in hex, and then let's compare it to what we hope is the same raw seed. It should be the same. Yes, okay, good. Next, let's look at the public keys. So for this, we can just have a look at the pair. On the pair, there is a function called public, which gives you the public key. There's actually one item in it that's publicly that's visible from the API. I think it's just a bunch of numbers. I think it's like an array, probably 32 bytes. There it is. And we can look at that in hex. Then we can also, as it turns out, pair the public key type. It's a special type. If we look at this, it has, I think, a debug implementation that shows us this hex, but also shows us the Polkadot or Substrate representation, or at least the first few bytes of it. There it is. So it elides the rest, but this is what you would be looking at if you're looking on like a Polkadot block explorer or whatever. But this is the hex of the public key. Yeah, and it's actually literally the bytes of the public key rendered as hex. It's nothing special going on there. And if we look at the same pair, this thing that we recreated from the mnemonic phrase, we should be seeing the same thing. And for that matter, let's that is the same thing, very obviously. We can compare them. We'll get true. If we want to actually just create the public key from this hex, apparently we can't compare them. Okay. Surprising. Anyway, we can see that they're the same anyway. I guess we can compare. That's because I'm not looking at the public key. If we introduce some extra crypto stuff, then we can recreate the public key if you're not familiar, hex is just a way of introducing hex literals as byte arrays. We'll put this hex literal in, just copy and paste it. And then we should be able to, oh, is it not going to like that? Yeah. Then we should be able to compare this public key. Hex literal. Do I have this imported? Hope I do. Apparently I don't. Let's bring it in. This is because I had an issue at the beginning and I probably didn't retype any of this stuff. So when it's doing this, it's actually like building everything again. I mean, it's cached, so it's faster than it would otherwise be, but still. All right. Now, once we've got this public key inserted, we can compare them, and it will work, I think. Now, the point of all this is just to demonstrate very clearly that these keys are just bits of data, they're blobs, right? We can work with them like we work with any other blobs of data. And if we know that this is the blob, if we know it's these I don't know, words for this phrase, or we know it's this public key, this hex blob, we can recreate it, we can compare them, and it works. It's nothing fancy is going on behind the scenes. There are no complicated types. It's all very very straightforward. So I want you're going to have to become pretty comfortable with working with this stuff. So it's important that you're not like scared of, I don't know, touching the wrong thing in the wrong way or something. It's simple, it's robust. Don't worry about it. Right, let's do something interesting. So we're going to take a phrase, in this case, welcome to Polkadot Academy 2023. And we're going to use the pair to sign it. Okay? And let's have a look at what we've got back. There you go. That's a signature. That's what a signature looks like, at least when you're using SR25519 cryptography. Okay? I don't know, 64 bytes, I guess. Pretty random, pretty uniformly distributed, pretty random looking. There's nothing special about this. You can recreate this signature from this data, right? Let's see if we can verify it. So the way we verify SR, we're going to have to go back into SR25519. It's a thing of pair. It's a function on pair. Verify. First, we give it the signature. Then we have to give it the same phrase. So let's put the same phrase in. Obviously, this is like we're verifying whether this signature means that this message was verified by the public key, right? So I don't know, public. We can use public. We could even use pair.public. They're the same thing, right? For now, we'll use public. Even though they came from like different, their heritage is different. Public was just something that we like typed in manually, and pair was something that we created on the machine. It doesn't matter which one we use because it's the same blob. Let's have a look, see if it verifies. We hope it would, right? We hope this does verify. It really should. There we go, true. Now, let's change it a little bit and see if it verifies still. So now the message is a little bit different. We're trying to verify whether this signature means that public key signed that message. No, it didn't sign that message. False. Good. We can maybe try it with a different public key. So it's a valid signature, but maybe we if we create another public key, this one is just a public key that is all zeros. It's a bit. Hold on. 259 public. We don't have a default public key, so we're just going to use unchecked from, which is a way of saying don't bother actually making sure this is a valid public key, just go with it, and we'll feed it 32 zeros for our public key. Now again, even though it's a valid signature, and it's a signature for this message, we're not giving it the right signer, and therefore it's going to tell us, no, this signature does not represent this person signing this message. So that's correct as well. That's good. And we can also alter the signature. So let's do that. Signature, and we're in SR25519 crypto. And again, we're just going to use unchecked from because we're not going to mess around, and it's 64 bytes. A signature's length is 64 bytes, so it's a 64-byte array of just zeros. Again, because even though this, actually I put the wrong thing in, haven't I? That should actually be 2023. Even though this message, 2023, was signed by this public key, this signature is not how they signed it, right? So it's again false. All three have to be correct, exactly correct, for this to return true. Good. One other thing, just want to demonstrate while we're here. We can make another signature. So maybe our identity signs another message. Welcome to Polkadot Academy 2022. And then we see, let's see if other sig works here. Like, again, in principle, it did sign this message, 2023, but we're using a different signature. One that was for the message 2022. Same public, both of them with the same identity, but no, still false. So really demonstrating that a signature by someone for one message is only valid for that message, even if they signed other things. It doesn't matter, right? Signature, message, and the identity are all required to be exactly right. Good. As I said before, some signing, some public, private key, asymmetric crypto, digital signature systems require a fixed length message, 32 bytes often. I think that's the case in ECDSA. Therefore, when we've got arbitrary sized messages coming in, or indeed any message that is not or might not be 32 bytes, we're generally going to hash it first. This is typically what you'll see with signing and verifying. It's got this hash in there. And this is one of the things that we mean when we say hybrid cryptography, right? We're using different cryptographic primitives to build better systems, composed from them. Of course, it is important that we use the same hash function. Yeah? Can't be just any hash function. It has to be the same for sign and for verify. Good. When a message is signed, this is not a silver bullet. There usually have to be rules about how this signature is intended to be interpreted and how the message is intended to be interpreted. Classic example, you sign please transfer $100 to Joe Blogs. I only mean for that transfer to be done once, right? Once. It should not be possible for someone to take this and give it to whatever digital system, blockchain, bank, doesn't matter, multiple times to keep sending $100 from my account to Joe Blogg's account, yeah? There is an expectation that a message, or indeed a signature, should only be used once. Yeah. We'll not look at this too much. But basically the point of this is not quite what I wanted to get across, but the main point is that whereas with encryption, we will tend to use, encryption is pretty much defined as using the public key first, and then the secret key on the decryption step. So we use the public key to encrypt, the secret key to decrypt. Signing is the other way round. We use the secret key to sign and the public key to verify. But they are, to all intents and purposes, the same operations. Mathematically, they're equivalent. Mathematically, decryption is the same as signing. Yeah? And encryption is the same as verifying. Like, it actually uses the same code beneath, under the hood. But we just give it different names because, We are engineers, and we're using the stuff. We don't care about how it's implemented. We have to be careful to avoid the same message, meaning possibly the same thing, possibly something else, on more than one system, in more than one context. Now, this is actually a general problem when using cryptographic primitives. It's a semantic problem. So it's not an issue with the primitives themselves, it's an issue with how they're used. If we sign something, it's important that that signature only carries weight in one context. Yeah? Because if it carries weight, if it means something in multiple contexts, then this single piece of information could possibly be maliciously reused elsewhere. In general, we need to introduce context into our message to ensure that the signature, to limit the context that the signature, to limit the situation that the signature can validly be used in. Yeah? To limit the meaning of the message, essentially. And this is used a lot in blockchain, but also quite a lot, in applications built on blockchain where that use some of these cryptographic primitives. Account nonces, these are basically just counters to prevent the possibility that if one transaction goes through, that same data cannot be reused in the same place. Because we introduce this counter and we require the counter to be part of the transaction and then part of the signing payload, it becomes invalid for it to be used a second time. Of course, if you allow the counter to be reset, then there can be an issue. And there are ways to manage this issue. Timestamps, another way of limiting the context. Yeah, you limit the period of time that a message may be useful for. Genesis hash prevents it from being used on alternative systems, like alternative chains. Each blockchain has a genesis hash. Some of them share them if they're hard forks. This can be a problem. Versioning, identifying more recent checkpoints in the system to prevent systems that have diverged the same message being used on both systems. Very important to introduce context when you're using signatures to mean things. Like, context must be in the meaning. Your meaning must be specific so that it's only usable in the system, in the situation that you intend it to be meaningful in. And for that matter, that no other system could accidentally have a user sign something that is useful, obviously, in that system, but also accidentally in the system you're developing. Yeah? So it's not, this is where you've got to be careful about message formats, yeah? Precisely what it is that the user is signing. You're generally just going to have to namespace everything. You're going to have to make sure that your application is part, some, format or identifier for your application that could never be accidentally confused with anything else is part of the message payload that goes into the signature. Okay, moving on. Hierarchical deterministic key derivation. So when we're deriving keys, we have you saw just before, we have this mnemonic phrase, this 12 words or whatever. And this contains the entropy. These words are randomly selected using, hopefully, some high-quality entropy. From these words, we're able to distill a secret, right? 32 bytes or whatever, that feeds into the cryptography and that we keep just on our machine, we keep under our ownership, and prevent anyone else from signing on our behalf or decrypting messages intended for us. Well, it might be that we want more than one key. It's all very well having like just one identity for everything, but oftentimes you don't want to use the same identity in one place as you do in another place. You might want to use a different identity for different systems, different applications, different blockchains, different levels of privilege. Like, I don't know, maybe you've got like a current account and a savings account. You might want different keys for those two accounts. It doesn't necessarily make sense to have one key for everything. Now, you could just derive different, just have different phrases for all the different keys, right? So you could just have, you maybe have 20 keys that you tend to use, you just have 20 different phrases. Each phrase derives a different key, you write them all down, keep them all safe. It's pretty cumbersome. So instead, what we do is we say, well, we'll just have one seed, one key, one phrase, and from that one phrase, we will derive many different keys. Yeah. And we can derive them through, well, we can derive them recursively. We have mechanisms for doing this. And as such, we can turn it into a hierarchical, like, kind of path. And we can sort of, from a path and a seed, we can derive a new key. There are two ways of deriving, roughly speaking, two ways of deriving keys. And they're very different. They come with different guarantees. We call them hard and soft. Hard derivation, when we sort of go down one of these tree nodes we go down one of these. So the act of getting from here to here, that's a derivation, right? That's a single step. And the step can either be hard or soft. Yeah. If it's hard, it's secure. It's more secure. It's very secure. It actually just uses a very simple way of deriving the new key from the old key. Basically, just hashes it with an extra like index or whatever in there, so you get just a new value. And because we use a secure hashing function, there's no way of taking this new secret and deriving the old one from. What does this mean? It means if the new secret is leaked somehow, maybe you had it on your laptop and your laptop was stolen and someone does a dump of the hard drive and they pull it off. If your new secret, your derived key, ends up being leaked, but your master key is still, I don't know, paper wallet or something, I don't know, it was not compromised, it wasn't on your laptop, there is no way of deriving these parents from this child, even though the secret is gone. Of course, this one is game over, right? Whoever's got your laptop can now control this account. Yeah, they can send messages from this identity, but they can't send messages from this identity or decrypt messages for this identity, and so on, right? This is what it means, hard derivation. Why not? Well, because when you hash this with an index and get some other hash, there is no way of reversing that, right? It's one direction, one way. Soft derivation, on the other hand, just want to go into this quickly before we dive down a little bit more. Soft derivation means that if your derived key is leaked and you happen to know the public key, so suppose again this derived key was leaked, and you happen to know the public key of this and the public key of this, and there's no reason that you wouldn't know the public key of these two, right? Because it's public, so you probably shared them. Then you can derive from the private key of this, the secret of this, the secret of this. So operationally, much less secure. However, it comes with some advantages, which we'll go into in a second. Pretty magical advantages. Okay. Good. So, yes, hard derivation. Generally going to use, most of the time you want to use hard derivation for operational security, because you don't want losing one key to compromise other keys. I mean, obviously, if you lose a key up here, then it's going to compromise all the keys downstream, yeah? Because that's the whole point. You can take this key, and you can derive all of these from it. So losing this key would be very, very bad. Losing the secret for this key would be very, very bad. Our main assumption is that this is very secure, these are a bit less secure, these are a bit still less secure, and so on all the way down, right? So we shouldn't care so much about if one of these are compromised, but we should make really, really well sure that this never gets compromised. Yeah? Because the power of this key is exponentially greater than the power of these keys. Yep, good. Right. Yeah. So oftentimes we'll actually use hard derivation. We'll always use it at the beginning of the path, and oftentimes we'll use it in order to actually split out the networks. So actually use hard derivation from a master key to split out keys for completely different contexts. Wallets, like multi-network wallets, will tend to do this. I will give a quick demo of hard derivation. Now, I'm going to fast forward, but let's just go through what the code is. So pair, that's our key pair. Derive, that allows us to derive a new key pair from it. The sum is, this next bit is actually just creating an iterator of derived junctions. So, can I do this? Yes. Basically, we're creating the path down. And each time we have a junction, each time we have one of these paths, it's a new item in the iterator. Yeah? So if the iterator is just one item long, which this one is, it will just be one derivation, the depth of one, if you like. In principle, we could have many. Good. So, derived junction hard, right? It's hard, not soft. Our index is we're actually giving it a name rather than a number. It's fine with that. The indices are actually all hashes anyway. They're all like 32-byte things. We turn it into an iterator. It's just an iterator of one item. None doesn't is fine, and then it's just unwrap it because it's a result. Look at the pair that comes out, which is the 0, and then we're looking at the public key of the pair. Okay. If we do this, and what this does is it tells us, essentially, if we imagine this line is labeled foo, it will tell us what the public key of this identity is, of this key pair is. Yeah, that's what that line does. And there you go. It's D2, ABC, blah, 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 blah. And in Polkadot, it would be recognized as, I think that's Polkadot. Maybe it's Substrate. Yeah, maybe it's Substrate. So in Substrate general identity, key identity, it would be 5, capital G, PV, blah, blah, blah. Good. Now, if we have the same key pair, we can derive it. We can derive exactly the same key. So all I need to do is write same pair there, and it will come back to the same key, demonstrating that there's not some crazy voodoo stuff going on. It's fully deterministic. Yeah. Even though I created same pair on a separate code path to creating pair, it's the same data underneath, and therefore it will derive the same keys. if we, let's think, right. Yeah, I don't think I need to do that one. Okay, if we derive a different path, let's go back here, we'll end up with a different key. So I'll just put bar in instead. So what we're doing here is essentially, we named this one foo. If we name this one bar, we're looking at the public key for this key pair. Okay? And there it is. And it's, as you can see, different to the first one's public key. Yep. Again, really not voodoo. That's the main point of all of this. Should become comfortable with it. Okay, good. So let's just go over soft derivation. Any network of soft-derived keys, any hierarchy of soft-derived keys are related, mathematically related. And we can see that they're related just by looking at the public keys that the accounts derive. So although the secret keys are related using soft derivation, obviously, we're generating new ones using the soft derivation function, the public keys of the accounts that are derived are themselves related in a very visible way. Yeah? This is why they can be useful. So a business might want to publish a particular address and then have users, have payees who want to give the business some money, each transfer into a different address, but an address that they know is still controllable by the owner of this main root address, this public address that they know. Yeah? So instead of sending to the public address directly, they send to an account that they know that public address controls. And they can know that it controls, they can actually mathematically know that they have control of it by using soft derivation. I'll give you a demo of this now. So we're familiar with the hard derivation, so let's do a soft derivation. We'll go back to foo, and instead of hard, just replace it with soft. And if we want to, there we go. Looks just like a hard derived one. It's a different thing, but it's the same type, right? It's a different value, but it's the same type. If we use a different, again, the same pair, but it came a different route through the system, it's still going to generate the same key. Now, let's do something clever. So we're going to let public, actually we already have public, don't we? I think it's just pair.public. Yeah. So let's take public, and we're going to derive a new public key. Derive, right? This is not a pair, this is just the public key. And we're going to derive the same junction. So I'm just going to copy and paste this thing in. And unwrap the result. And you see it's the same as before. So this one was when we took the key pair, like the secret, and derived a new secret called foo on the foo branch. This one, we didn't have the secret, we didn't have access to the secret, we only knew the public counterpart, and we used that to derive the foo child, and we ended up with the same thing. The public keys are related through the relation of the secret key when we use soft derivation. And this relation can be used such that if this derived secret is known as well, along with the 2 public keys, then we can calculate the parent's secret, right? And if it goes all the way up to the root, then we can calculate the root's secret, and that's very, very bad. So this is why we tend to use hard derivation paths almost all the way down, and if we need the public keys to be relatable, then we might use soft paths at the end, soft derivations at the end. But in general, we don't use soft derivations for most typical uses. But there will be uses where this is a very useful, there will be instances where this is a very useful solution, a very elegant solution. Right, that's all I have to say on that for now. So, mnemonics and seed creation. We saw the mnemonic before, 12 words, oftentimes it's 24 words. Again, this is due to the entropy contained within. 24 words, I think, can hold about 256, maybe a little over, bits of entropy. 12 is less. 12 is still basically secure, but, you know, if you want to be like actually secure, 24 is better. There are standard dictionaries, Bitcoin or the Bitcoin community proposed one, and I think most of them use it. Most systems use it. BIP39, if you're interested. These BIP39 also tells you how to turn a phrase into a key, a 64-byte key in this case. And you just basically put it through a bunch of times around the SHA-512 function, right? So you throw it into a hash function, throw the result back in, keep spinning on that like a couple thousand times, and that's and you end up with the final key. Yeah, key derivation is fairly standard, but not very standard. There are actually several standards for turning a mnemonic into a private key, into a secret key. And different wallets will support a different set of standards. And for this reason, you can often find that an account made in one wallet is inaccessible in a new wallet that you kind of want to try. And it's a big pain. And you do get like ways of moving between things and translating, but it's a bit of a pain. Yeah, you know, it is what happens in open systems, I suppose. Okay, let's look at some of the signature schemes. ECDSA, Bitcoin and Ethereum used it. It's a bit old now, a bit long in the tooth. Uses this curve, the Koblitz curve. There is another curve, B1, P1 maybe. This is the main difference between these curves, point of trivia. The Koblitz curve has no funny numbers in. So the Koblitz curve is basically all like prime numbers and, I don't know, you know, small, very, very small numbers. There's no like entropy in these numbers. No one could have fudged the numbers in order to make it easy to hack. Whereas the other curve, the NIS curve, I think, the American government backed curve does have a bunch of funny numbers in. Looks like it's maybe been optimized a little bit for something, but no one's quite sure what. This is the reason why, you know, in Bitcoin and Ethereum chose not the government curve, but the mathematically elegant curve. ECDSA, as I said, it's a bit long in the tooth now, it's quite old. And things like threshold signatures, something that we'll get into a bit later, are not made particularly easy by it. And there are now, like, you know, such things as Schnorr signature. Well, I mean, now we can publicly use Schnorr signatures. There's a patent on it until not that long ago that allowed us to use quite advanced cryptographic features like threshold signatures. ED 25519 is basically it uses the Edwards curve, that's the ED part, and it uses Schnorr signatures to do its signatures. It's pretty fast, like 20 to 30x faster, pretty good speed up. And it's a bit more useful for doing some more exotic things, like threshold signatures. SR 2519 is the Schnorr ristretto. That's what the R stands for. It's a slightly tweaked version of ED 25519. Removes some of the some relatively minor but still present risk factors and makes it more useful for certain features that we want to use. I think ED 25519 is still useful for verifiable random functions more so than SR 25519 for what it's worth. Both are used. Both ED and SR are used in Substrate, but they have almost exactly equivalent APIs, so if you know how to use one, you can use the other. Here we go. So SR2559, default key type, public key is 32 bytes, much like ED 25519, used to identify key holders, like account IDs are these 32 bytes. We do also allow SECP 256K1, so this ECDSA, this like older type of signing cryptography. But annoyingly, the public keys are 33 bytes, and again, like not necessarily with well-distributed entropy. So we hash them when we use them to represent an account ID. We get a 32-byte account ID from it. Our assumption is, and it's a reasonable one, is that the hash of one of these public keys is unlikely to ever collide with the public key from SR 25519 or ED 25519. I mean, a hash pre-image attack, you know, or a collision, it's possible, but you know, these things are meant to be basically uniformly random, and these things are basically meant to be uniformly random, so probably fine. Good, right. That's the end of that lecture. I'll take questions on it. Wow, no questions.
Hello. When I create a key in a wallet, how do it just outputs a pair. How do I know that it doesn't already exist? Like I always wondered about that.
You don't. And in fact, it might. It depends on the wallet, of course. But this is the whole point of that conversation on entropy. You know, entropy is how predictable some particular, I mean, it's the amount of non-redundant information content. If that wallet always gives the same key, no matter how like random it looks, it's still very predictable, right? It still contains essentially no information. It has been in the past, but I think there was an example of a web-based wallet that did tend to give the same keys. Like there was a lot of key reuse, just because it had a really broken random entropy collector. I think it used the mouse, but it like used it in such a way that it didn't, like many people used the mouse waving in roughly the same way, and it threw away much of the high entropy information, and you ended up with many different people having the same public key. If you're being paranoid, check the source code and compile yourself. Make sure that it's using the operating system's like secure random number generator. Most modern operating systems do have a sort of secure random source. And I say secure, if you remember on the list, there was like 4 items, and secure operating system secure is like the 3rd item. It's reasonably secure. a determined attacker who has some degree of control over your hardware might be able to bias it. But for most people, it's probably good enough. If you're really paranoid, get a hardware device. If you're ultra paranoid, buy a hardware device making company and all of the companies of their supply chain. Check everyone's designs. But I mean, you know, not many people are that paranoid. Yeah, sure. If you want to spend quite a long time, you can also roll some dice. I mean, you need, I don't know, how many bits, like 256 bits of entropy, let's say, for one key. And a die, I mean, if you do coin flips, then you just have to flip a coin 256 times. I mean, it would get tiring after a while. It'll probably take you an hour or two, but you know, that's definitely random, yeah? I mean, is it random? I think as long as you close your eyes when you're like resetting the coin, it's probably random. Some people have biases to like have heads on top when they flip it or something. And apparently when you flip a coin, it actually many times only flips once before it comes down. But, rolling a die, yep, sure. You get maybe 2 and a bit bits, so you only have to roll a die like 100 times or something. Okay. 16. Is there a D16? I've never seen a D16. I've seen a D12, D20. But you can, sure. So it's certainly a D8, right? So you can get 3 bits from a D8 die roll. It's going to take a while, but sure. If you've got an hour to spare and you're really desperate, that only works for one key, of course. If you're trying to generate like multiple keys for some reason, then it's a bit difficult. Yeah, I think that's... Was there another part of the question?
Yep. Well, the Rust demo that you did, is that available anywhere in the course material?
Yeah, we
with
can
all
make
the
that
commands?
available. Sure.
Okay, yeah.
So what protects me from someone generating an address and falling on my address by hazard? Like they have access to all my funds. What is there a protocol to protect me from this?
Right, so you can generate a secret. This is your secret. You don't tell, this is like a number, it's a long number, but it's still a number. We saw what the numbers look like. It's a long number, but you keep this secret, right? Now, if you're doing it properly, you do it on a device that will never be online, right? Like a phone with its aerial ripped out, or a piece of paper or something. All right, so you've generated your secret. Now, this secret has the power to authorize, to sign, basically to authorize instructions of the counterpart public address, right? There is a single counterpart public address for this secret. Someone else can generate an account, a secret, but it won't be of the same address. It won't be for the same address. It will have its own address. Yeah? All secrets, a different secret will have a different address. Now, this is assuming that you're using a secure way of generating secrets. If your way of generating secrets is, I don't know, take the current day, month, and year, then on the same day, everyone will have the same secret. Maybe that's done. Maybe you take the location and minute, hour, day, month, year, right? But then anyone in the same location on the same minute or the same 60-second interval will get the same secret. Now, I don't think anyone's been as stupid to use that algorithm, but there have been flawed algorithms out there, flawed web pages for generating secrets. And if that's used, then it is conceivable that 2 different people would have the same secret and therefore have the same address. And if this is the case, it's hugely problematic because, as you say, if someone, puts money in if person A puts money in their account, well, person B can now access that money. This is definitely the exception, right? This is not intended behavior. This is what happens when you have a broken secret, a broken key generation software or broken random number generator.
Okay, thank you.
Would you mind going back to the REPL to show what you did on the soft derivation? Because I was wondering if you showed that you could get the. So can you just describe the last few lines again? You're taking the public key of the parent and child to derive the secret, or am I missing something?
Right. So we have the key pair. Here. Actually, let me highlight with the cursor. So we have the key pair here. Right? This is a key pair that we derived a while back. We have the mnemonic. It's this mnemonic. Come on. It's compiling everything. It's like, yeah, okay. Mnemonic every time. It's Rust. It's very good for correctness, not so good as a shell. Okay, so this is the mnemonic, right? And we use this mnemonic to make a key pair. So this is our random material. No one should have these 12 words. Like, no one should know these 12 words. It's like a super password. All right. And we used that mnemonic to make this key pair, right? It didn't actually come from that mnemonic, but when we made this key pair, it told us, if you want to make this key pair again, this is the 12 words that you use to do so. And then we did make another, we duplicated this key pair by using this mnemonic, and we called it same pair. Right, so we've got pair. We're deriving a new key from it. To derive a new key from it, we give it a bunch of junctions, right? We tell it, a bit like when we got a directory, like a file name, right? And we go, slash, I don't know, user slash local slash doc. So each kind of directory junction is like a derivation junction. Yeah. In Rust, this is just Rust syntax. If we want a iterator of a single item, then you can just write sum the item dot into iter. That's just a Rust trick. So don't get too confused about that. And then the item is this. Derive junction. Surprisingly enough, that's just a junction, right? Soft. So we're telling it we want a soft derivation. And then every junction has a name. Otherwise, we don't keep track of any indices, obviously. So we need to give it some sort of reference. Otherwise, we'd only ever be able to derive one thing. So we give it a name. The name in this case is foo. So that's what we're doing. We're deriving it from the pair. Now, you can assume this pair basically means the secret. When we're working with a key pair, the important bit is the secret. We can always derive the public from the secret, probably. So when we're working with a pair, we mean pretty much the secret. If this were public, then we'd only have the public key available, and we'd be working with just the public counterpart. Okay. The rest of it, we're going to unwrap. Fine. 0 just gives us the key pair. I can't remember what the other items are. It's in the API. And public is the public part of this new derived key pair, right? And we're just going to look at what it is. So we're taking the secret key, deriving, using the soft method, one level down on the branch foo, and then we're looking at what that public counterpart is. Come like that, and we'll get, I think, it was here. I think it's just this 54D39. Yep, there it is. Now, what we can do... Oh, that's not what I wanted. That's what I wanted. Now, let's look at this line. This is not the secret. This is the public key. Yeah? So we're not working with a secret key at all. We don't know the secret key. This could just as well be written by anyone on the internet that I happen to, assuming I publish my public counterpart, hey, this is me, this is my identity, then anyone could would just use that identity as the public key. Yeah? We're deriving a new public key from it, Public keys only derive public keys. Secret keys only derive secret keys. I mean, and their counterpart public. So we're deriving a new public key with it, using the same junction, soft, foo, yeah? And then we're just looking, seeing what it is. It's a result, so we have to unwrap. And it will give us the same public key. What it's saying is that if we take the secret and we derive the foo child and look at the public key, it's the same as taking the public key, deriving the foo child of the public key, and looking at it directly. So it's like there is a magical relation between the public key and the secret key, such that when we derive new secret keys, their public key is exactly the same value as if we derived just the public key. But yet there's no way of getting from the public key back to the secret key. So there's this like relationship that is not one that you need to sort of go back and through the other way. It's like a parallel information relationship. You don't really come across it much in other areas of life. I think you probably do in information in mathematical-based information systems. But this, I certainly hadn't seen anything much like this when I came to it. And it's an important thing to understand, right? Because with this is the sort of primitives by which you can build quite sophisticated systems that are trust-free, right? They're trustless. We don't need to trust any particular person to operate the system correctly. This works purely because of math. And it's like, as long as there are no major mathematical discoveries or, quantum machines become viable, then this will hold. This relationship will hold. And that's, yeah, pretty cool. Yep.
Could you give some examples of when you would use derivation?
Yeah. I mean, hard derivation you use all the time. It's just like you only want to record, like, you should keep a backup of your private key, of your mnemonics, right, of your 24 words. And honestly, it's like a bit of a pain to write 24 words down and then like keep it somewhere safe, especially if you're like traveling a lot. It's like, where do you put it? Like in your back pocket? Oh, then it gets put in the wash and it's like, oh no, I can't read them anymore. So like, you've got you don't want to have too many of these like bits of paper floating around with 24 words on. Ideally just one. And what this allows you to do, like with hard derivation, is just have that one bit of paper and you keep it super, super safe. You never take it out. And you only like have, and maybe you have like one of the derived paths on a signing device, like a mobile phone, and then you derive a bit deeper, it's a bit more insecure, and you have that on a hot machine like your laptop, and so on. So this is where like hard derivation is super useful. Soft derivation is a bit more nuanced because it comes with this like very strange magical relationship. Here's an example. You might, suppose you want to like send someone some money, but they're offline when you want to send them the money. You don't want to send it into their main account because of privacy issues, right? They don't want to receive the money into their main account because it's where they receive a bunch of, pay their bills from and all the rest of it. So they want to receive it into some account that they control, but not their main account. So the way that you'd normally do it is just say, all right, make a new account for me, like derive a new path, so you got a new secret or whatever, and tell me what that is, and I'll send the money there. But here's the thing, they're offline, so you can't do that. So then what do? You have to send them the money, but you can't negotiate an address for it, and they don't want to receive it in their main address. Well, you can use soft derivation to create a new address that you know that they control, but that no one else knows they control. How? Well, you take the public key, right? This is an account that is identifiable with them, right? You then take a hash of the transaction. Maybe it's an eBay purchase or something like this, right? And it's got like an invoice number or something. But it's got some sort of identifier that identifies this specific purchase or transaction, and you hash it. You then use that as the derived branch name, right? So in this case, we used foo, but it can be any length, right? Because we're just going to hash it anyway. So you take the account, you take this invoice ID or whatever it is, and that they would know, but that no one else is likely to know, and you use that. Well, you would use it on the public derive. You use that here. You derive a new public key, and you send the money there. Now, to everyone else who doesn't know that you've combined the invoice number with their public address, it just looks like another random account that's received some funds. Yeah? But to them, they can just scan through all their invoices, generate all the receiving accounts, and check to see if any of them have received any funds. So when they get home, they get in. Maybe they've got an email from you and you've said, I sent it to this derived account. Maybe you don't even do that. Maybe it's just a convention. And they just have a script that goes through all of these public addresses and checks to see if any of them receive funds, realize that they have one from you. They have the secret, so they can derive the secret key pair, and they can take the money and put it wherever they want.
So it's for preventing doxing.
It provides some degree of privacy, but it's also more for like building. This is just one example, but there are sort of many different examples where it's useful for the public keys to be related. It's useful for another example would be where you've generated a new public key, and you have some. You've correctly, you've put it out there. This here, this key pair, this public key, this is me. I am Gavin. Gavin is this key pair, right? That's my online identity. Now I could generate a new key pair using a hard derivation, but no one could verify that that is me, right? I'd need a certificate, basically. This account would need to sign some witness statement to say that that new account is definitely me. But maybe I don't, that's extra complication. I could also just use the public key, which people know is my public key, and I can say, well, I've got this other account, but it's a soft derivation. Using a soft derivation, I can show that only I could possibly be in control of this account, just by letting you know what foo is, so you can verify that my public address, when I derive on the foo branch, you get this second address. You can see that only I could possibly control that second address. So I don't need to issue any certificates. It's just another one of my accounts, and I can, it's intrinsic, it's inherently demonstrable that I control this second account in a way that a hard derived path can never be. For that, we would need an extra mechanism like a certificate. So there are like it's an abstract. It's like a facility. It's a relationship. It's a property. It can be useful. It can be dangerous, and it's something to be aware of, to use or to definitely not use, depending on whether for your use case it will introduce too much danger or it will actually be useful.
Thanks.
Actually, I might have a follow-up on that one. It's real quick. So if you lose one of the soft-derived private keys, right, then the public, if that one is lost, everything back up to the root of where that the last soft-derived key is lost as well, or could be compromised?
Right, so yeah, it's not so much about losing. If you lose your bit of paper, I mean, if it gets burned, like goes up in flames, then that's not a big problem. But yeah, if it's compromised, if someone else knows it, then all the way up, using soft junctions, yeah, the secrets are potentially compromised. The attacker would have to know the path names, right? So they'd have to know that, basically like the public keys. But if they know this information, yes, they can derive the super key from the subkey.
So multiple soft derivations of keys is probably a bad idea. Like, at least
When using soft derivation, yes. You probably just want to do it once for a specific use case and only at the end.
At the beginning of a Rust demo, you typed the let per mnemonic row seed SR25519 per generate with phrase none. And
Okay.
I know this is a dumb question, but I have to ask. So what is the chance, what is the possibilities if some, let's say, D-app is using this kind of, some app is using this none to generate a seed phrase? No, not this one, the one that you generate the mnemonic. Actually.
Okay, so one above. Where were
Yeah,
we?
up there, the first one.
Generate your phrase. This one?
Yeah, yeah. So what is the chance, and if it can happen, what is the protection mechanism that it will not generate the same mnemonic?
Well, again, it does depend on the. I mean, this uses system random input, right? So it's using the most secure stream, random input stream that the operating system can provide. So the chances are minimal, right?
Still there are.
I mean, there's a chance that you'll just guess my secret, right? Like you guess the lottery, yeah? It's unlikely. I wouldn't like, cross your fingers, hold your breath or anything. Yes, it's possible, theoretically. But a lot of crypto is theoretically compromisable just by luck. But I mean, being that lucky, we can quantify how lucky you would have to be, and it would be like more lucky than anyone has ever been, ever, and is ever expected to be in the next 10,000 years, right? So we're reasonably happy with the possibility that, striking off this possibility. Okay.
Just wanted to quantify that number. I think if I remember correctly, like 2 to the 256, like a 256-bit secret key, is on the order of magnitude of the number of particles in the universe. So if you had one guess for every particle in the universe, one of those is your key. And the biggest bug bounty in the world is Satoshi Nakamoto's keys. Like if you think you found a way to hack the hashing and the security, all the stuff, if you know Satoshi's keys, you have access to his Bitcoin, right? So this stuff is like blockchain in many ways is very much like an open honeypot. Like if you can break this, you not only have access to all that money, but probably there's a bunch of NSA secrets and a bunch of other things that you can have access to too. So this is like pretty, last Academy, you said this is not difficult or hard. This is like the scientific difficult or hard. This is not this is a hard day's work. This is literally like mathematically hard, right?
Yes, it's we use relatively modest terms because this is it's a good course. Yeah? We don't want to overstate things, but we are working in the realm of mathematics, the realm of science. So when we say it is hard, we don't mean it'll take you a few hours if you knuckle down, right? We mean humanity has not solved it. There's maybe some. So yeah, as Sean said, if you want a more real practical benchmark on guessing. So these keys, you got 2 to the 256 possible keys, right? Basically 2 to the 256 possible mnemonic phrases. So guessing these 12 words. I mean, it seems maybe it wouldn't take that long to guess. They all seem like reasonable words. How many words can there be? I'll just try all of them, right? But, there are 2,000 odd words in this dictionary, and it's any 20 in this specific order, right? And it turns out it's about 2 to the 256 combinations. I think we assume that if the American government put serious funds in, they could maybe make 2 to the 50 or 60, like that kind of order of magnitude, number of guesses, right? And that will go up each year because computers get faster. But still, it's orders and orders of magnitude below this 2 to the 256. And even if you got like using the birthday paradox, so you can half that, yeah, so you're actually only looking for collisions rather than a pre-image attack, you're still, again, many orders of magnitude from being able to achieve anything with conventional hardware and a realistic budget. I mean, if Satoshi's Bitcoin accounts became worth, tens of trillions, and the Bitcoin market had depth of tens of trillions, then it might actually be worth, I don't know, like a world government, I suppose, to invest in a supercomputer that would crack Satoshi's keys. But we're nowhere near that point yet. Okay, good. That's all of the lessons for today.